Hi everyone. Today we're going to talk about angles of elevation and depression and kind of tie together some of our trigonometry conversation. So an angle of elevation is the angle formed by a horizontal line and a line of sight to a point above the line. So what this looks like is if I have somebody who is looking straight out horizontally, then the angle of elevation is created with that horizontal line and a line of sight to something that's above that line. So this is an angle of elevation. It's created by that horizontal line and a line of sight to a point above the line. Now an angle of depression is a little different. It's an angle formed again by a horizontal line and a line of sight to a point that is below the line. So again, we have somebody looking straight out horizontally, but then the angle of depression is formed by that person then glancing down at something. So that's an angle of depression. An angle of elevation is created by the horizontal line and a line going above, and the angle of depression is created by a horizontal line and another line going down. And I guess in this case I'm talking about segments, but in general I'm talking about kind of these lines of sight that we have here. So imagine that as you look places, you're creating almost like a ray from you all the way out, extending to infinity in a certain direction. So underneath, we've got a little picture to help you classify angles of elevation and depression. There are 4 different angles here. And before we begin, I want to label some things. So it's going to make our descriptions a little bit easier. So this guy, he's got some lines of sight coming out of his eyes. So this we're going to call Bob. Up here in the tree, we're going to say that there is a bird at that vertex. And then down here, all the way at the bottom, we're going to say there is a bug. All of these things, the bird, the bug, and Bob, can all look places. They all create lines of sight. And they're going to be the vertices for our angles of depression and elevation. So, in angle 1, here's angle 1, notice that it's created with a horizontal line, and then a line that is to something that is underneath the line. So that's an angle of depression. Well, what is at the vertex of that angle? Bob, the bird, or the bug? The bird. The bird is at the vertex of angle 1, and so the bird is doing the looking. And what is the bird looking at? If he's looking to something below the horizontal line, he's looking at Bob. So this is the angle of depression where the bird is looking to Bob. Bird to Bob. Okay. Angle 2. Angle 2 is created by this horizontal line of sight right here, and then a line of sight to something that is above the horizontal line. So that is an angle of elevation. So look at the vertex. Who is doing the looking? Whose line of sight is it? Well, it's Bob's line of sight. Bob is looking horizontally and then up at the bird. So this is the angle of elevation from Bob to bird. Angle 3 is right here, created by this horizontal line of sight, and the line of sight from Bob all the way down to this bug. So this is an angle of depression. From Bob at the vertex to bug. And then finally, we have angle 4, which is right here, created with this horizontal line of sight and this line of sight up here. So this is an angle of elevation because we have this horizontal line and then this line above. So this is elevation. and look at the vertex, whose line of sight is it? It's the bug's line of sight, and the bug is looking to Bob. So bug to Bob. Okay, so now that you have an idea of how to classify angles as angles of depression or elevation, it is important to talk about how there are angles that are neither angles of elevation or depression. For example, this angle right here that's created by Bob's line of sight to the bird and Bob's line of sight to the bug is neither an angle of elevation nor depression because it's not created by a horizontal line and then another line of sight. So angles of elevation and depression are always created by a horizontal line of sight and then another line of sight above or below it. But this itself, that's made up of angles 2 and 3 together, that is neither an angle of elevation or depression. So angles do exist that are not classified as elevation or depression. Now in this bottom problem, we'll come back and talk about it in a moment, but this is a bad question. So maybe label it bad question and move on. And we'll talk about why in a moment after we've done a few and practiced making our drawings and labeling them. So go to the next page. Okay, so if you notice, all of these problems today don't come with pictures. They're just blurbs of words describing a situation. And so one of the things that you're going to have to do is provide pictures for these problems. So if you are an artist, great. If you are into stick figures and that's your limitation of artistry, then you're in the same boat as me. So in the first problem, it says a forest ranger in a 90-foot observation tower sees a fire. The angle of depression to the fire is 7 degrees, an angle of depression. What is the horizontal distance between the tower and the fire? So let's draw the observation tower that's 90 feet high. Let's draw the fire that's far away. Let's put the angle of depression in the diagram. So here's my tower. And maybe he's, I don't know, maybe he's laying on his belly and he has binoculars. And he's looking out on this 90-foot observation tower and he's looking at a fire. And the fire is all the way over here. And so I have my 90 feet for the observation tower. I have the fire at a distance, and I need to draw the angle of depression to the fire. Remember that the angle of depression will be formed by a horizontal line and a line of sight to something below the horizontal line. So coming from his sight, from his eyes, I have a horizontal line. And then I have a line of sight to the fire below. And typically when we draw, we're going to draw these lines of sight to the very base of whatever they're looking at. Because usually you're going to have a picture set up like this. So don't draw the line of sight to like the middle of the fire, draw it to the very beginning so that you can stay consistent. And that angle of depression is 7 degrees. Now our pictures aren't going to look, exactly accurate. It doesn't really look like a 7-degree angle. However, the horizontal line of sight and the line of sight below that should create a 7-degree angle. Now, I need to put some other things in my diagram. For example, if the tower is built structurally well, then it should be making what kind of angle with the ground? It should be making a 90-degree angle with the ground. In addition, if the tower is have this line right here, well then I should also have a 90-degree angle right here. So one of the nice things about this situation is that in addition to this 7-degree angle, I can also come up with the angle measure for this angle by taking 90 and subtracting 7. So this angle right here measures 83 degrees. Now notice that in my diagram, what I have is a right triangle, and I have a lot of stuff around my right triangle to make my picture, but I do have essentially a right triangle that I can perform trigonometry with. And what I'm trying to find is the horizontal distance between the tower and the fire. So here's the tower. Its base is right here. Here's the fire. Its base is right here. So what I'm trying to find is this distance, a side length of my right triangle. So I'm going to do what I've been doing for the last few days. I'm going to take my angle and I'm going to draw an arrow all the way across. I'm going to label this side the opposite side. I'm going to label the hypotenuse across from the right angle the hypotenuse. And then I'm going to label this side the adjacent side. I'm going to think to myself, okay, SOHCAHTOA, which sides do I have measurements for, or do I need measurements for? I need the opposite side's measurement. I have the adjacent side's measurement. So if I'm using opposite and adjacent, the trigonometric ratio that uses both of those is tangent. So my equation is made up of tangent of my reference angle, 83 degrees. It equals the ratio of the opposite side, which is x, over the adjacent side, which is 90 feet. I need to isolate the x so I can solve for my side length. So I'm going to multiply both sides by 90 feet. And x, my missing side, is 90 times the tangent of 83 degrees. And it's a side length, so I'm measuring in feet. I could also round this answer. Could type it into Desmos, make sure that my Desmos graphing calculator's settings are set to degree mode. So 90 times the tangent of 83 degrees would be approximately 732.991 feet, which is reasonable. If your observation tower is 90 feet in the air and you're really looking, you can spot something that's a little over 700 feet away. So now you have the idea of what your pictures are going to look like and all the items that you need to put in them. So let's go to the next problem. Suppose that the ranger sees another fire and the angle of depression to the fire is 3 degrees. What is the horizontal distance to this fire? So it's the same ranger. Same ranger is sitting in the same observation tower, 90 feet in the air. We just have a different angle of depression now. The angle of depression is not 7 degrees, it's 3 degrees. So some items are going to change in our picture. So let's draw a rough sketch of our picture. So here is the observation tower. Here's the binoculars. His feet are a little strange. He sees the fire. He's 90 feet in the air. This fire is different than the other fire, so the distance from the observation tower to the fire is not the same. The angle of depression is created by a horizontal line and a line of sight to something below that horizontal line. So that's all the way down here to the fire. Now, something that students make a mistake on in their diagram is their 3-degree angle. Sometimes they label here, and that is incorrect. The line of sight to the item below and the horizontal line of sight, those are the things that create the angle of depression. So this is the 3-degree angle. Now, we still have a right angle. We still have a right angle here. This angle measure, though, is a little different. It's not going to be 83 degrees. How many degrees is that angle measure? Well, 90 minus 3 is 87. So this is an 87-degree angle. And I'm still asked to find the horizontal distance to the fire. So I'm still finding the same section of my right triangle. So I'm going to label like I did before. My reference angle is 87 degrees. All the way across from it is my opposite side. This is my hypotenuse. This is my adjacent side. I'm still looking for the opposite side, and I'm still given the adjacent side, so I'm still using the tangent trigonometric ratio, or trigonometric function. Angle is now 87 degrees instead of 83 degrees. My opposite side is still x. My adjacent side is still 90 feet. I still need to multiply both sides by 90 feet so that I can isolate my side length. So the length is equal to 90 times the tangent of 87 degrees measured in feet. Or, if you type it into Desmos and you round to the nearest thousandths place, you get a fire that's 1,717.302 feet away. Now think about if that's reasonable or not. This angle of depression was 7 degrees. And the fire was just over 700 feet away. This angle of depression was not as much. So that means that he's looking a little bit further than he was before. And that's good because our number is a little bit bigger than it was before. So that matches. That's reasonable. Let's look at our next problem. I'm going to read it. And maybe you can pause your video and you can see if you can get the diagram before I draw the diagram. The problem says that a pilot flying at an altitude of 2.7 kilometers sights two control towers directly in front of her. The angle of depression to the base of one tower is 37 degrees. The angle of depression to the base of the other tower is 58 degrees. What is the distance between the two towers? The distance between the two towers. So perhaps you can pause your video and you can try to draw kind of a crude diagram. If you can only get so far, that's all right. So just pause your video and try to draw what you see from the problem. Okay, if you're back with us, the pilot is in an airplane because they're flying. So you should have some kind of airplane. Okay, so there's the airplane. And the pilot is flying at an altitude of 2.7 kilometers. So the airplane is 2.7 kilometers from the ground. And because this is an altitude, we know that it's at a right angle with the ground. So that's important. And the pilot sights two control towers directly in front of her. So there's two control towers here. The angle of depression is given from the pilot to the base of the towers. So I'm going to go ahead and draw my horizontal line. And then I have two angles of depression. One of them, the smaller of the two angles, is to a tower and it's 37 degrees. So that would be to the tower that's further away. Remember, it is to the base down here. So this is 37 degrees. And then the other angle of depression is with the horizontal line and then the line of sight to the base of the other tower. And that is 58 degrees. And I need to know the distance between the two towers. So we have a lot that's going on here. Now, there are two distances that we're going to talk about to get our answer. And those two distances are down here. We're going to have this distance. Oops. because we have this right triangle. So maybe we'll call this x. And then we're also going to have this distance for this right triangle. See how we have two right triangles? So maybe we'll call that y. And I need to take a moment to label what's happening in these. Well, maybe not to label what's happening in these, but I need to take a moment to label my angles that are in my right triangle. So remember that we've got a 90-degree angle here. If I take 90 and I subtract 37, then I'm going to end up with a 53-degree angle. So this, starting here and going here, that's 53 degrees. And then if I do the same thing, but I'm trying to find this angle measure, then I'm going to do 90 minus 58. And when I subtract, I get 32. So this, lots of arc marks here. 1, 2, 3, 4. That is 32 degrees. So let's start out with this right triangle that's kind of on the inside. It has a 32-degree angle. So I'm going to go to the opposite side and label it. This is the hypotenuse. This is the adjacent side. I'm trying to find the opposite, and I have the adjacent. Opposite and adjacent is used by the tangent function. My angle of reference is 32 degrees. It's equal to the ratio of the opposite side, x, over the adjacent side, 2.7. I need to isolate the value of x, 7. And I have that x equals 2.7 times tangent of 32 degrees, and I'm measuring in kilometers. So I have one distance. Now I need the other distance, y, so that I can take the x and the y values and I can subtract them and find this distance between the two towers. So again, I'm going to go from my angle of reference to my opposite side. This is still my hypotenuse. This is still my adjacent side, so that works out nicely. I suppose here, opposite. I'm still looking for the opposite side, still giving the adjacent. So I'm using tangent again. This time my angle of reference is 53 degrees. The opposite side is y. The adjacent side is 2.7. I still need to isolate, multiplying by. So I have that y equals 2 tangent of 53 degrees, measures. And in the end, my final answer comes from taking my longer y distance and subtracting my shorter x distance. So y minus x equals 2.7 times tangent of 53 degrees minus 2.7 of tangent, 2.7 times tangent of 32 degrees. And this would be my exact answer in kilometers. If you to type this into Desmos, you would get an estimation, a rounded estimation of 1.896 kilometers apart. Okay. So our last problem today is a pilot that is flying at an altitude of 12,000 feet. So again, pilot. Flying at 12,000 feet. Sights two airports directly in front of him. So airport 1, airport 2. The angle of depression to one airport is 78 degrees, and the angle of depression to the second airport is 19 degrees. So here's my horizontal line of sight. I have one line of sight going to the first airport and one line of sight going to the second airport. The smaller angle of depression is 19 degrees, so that's going to be right here, 19 degrees. The larger angle of depression is 78 degrees, so that's going to be the one that's a little bit bigger, 78 degrees. And again, I need to know the distance between the two airports. So this picture looks great. However, it's unfinished with its labels. I need the labels for this angle and this angle. I need to know the distance between the two, so I need to put some labels on the bottom. And so what I'd like for you to do is pause your video, try this problem now that you have kind of the rough diagram. So try the problem, and then once you finish the problem, turn your video back on and see how you did. So check your labels, check your opposite and adjacent and hypotenuse labels. Make sure you use the tangent function. Notice that I also changed how the answer was written. So if we have 12,000 times the tangent of 71 degrees minus 12,000 times the tangent of 12 degrees measured in feet, then you can kind of factor out that 12,000 and let it sit out here, and then just have 12,000 times the tangent of 71 degrees minus the tangent of 12 degrees feet. And then this is the decimal rounded to the nearest thousandth. So before we end the video, I want to go back and look at the bad question. And I want to talk about why it is a bad question. So it says an air traffic controller at an airport sights a plane. So the air traffic controller at an airport sights a plane. So there is a plane in the air somewhere. At an angle of elevation of 41 feet. Or sorry, 41 degrees feet. Good grief. So here's my horizontal line. Here's my line of sight to something above, so 41 degrees. And the pilot reports that the plane's altitude is 4,000 feet, which is easy enough. And I need to know the horizontal distance between the plane and the airport. So I would need to know this distance. However, this air traffic controller that's sighting this plane, is the air traffic controller on the ground, laying on his belly? Or is the air traffic controller in a tower? So do you see the issue? We don't know how high up in the air this air traffic controller is. So we don't know whether we should draw the plane's altitude of 4,000 feet from the plane to here or from the plane to down here. And if we draw it from the plane to down here, well, we really don't know how high the air traffic controller is in the air. So that's why this question is a bad question. It doesn't give you as much information as you need.